Our next presentation is how will my phosphorus permanent limit impact our treatment plant. We advertised that Fred Mueller, the principal engineer for Ty and Bond, was going to speak on this topic. He's got a substitute, a fill-in. Ian Catlow, PE, senior project manager, will be speaking. Ian is a senior project manager for Ty and Bond. He has over 18 years experience in design, construction, operation of wastewater treatment facilities with specific focus on nutrient removal, upgrades, water reuse, and decentralized systems. He recently completed low-level phosphorus projects in Sturbridge and Wayland, Mass., and is currently leading nutrient removal projects in East Greenwich, Rhode Island, and Somerset, Massachusetts. Ian holds a bachelor's and master's degrees in civil engineering from Worcester Polytechnical Institute. He is an active member of NUIA's Asset Management Committee. So I'd like to welcome Ian.
Thanks for the introduction, Tom, and thanks for the Disney travel tip, too. I'm headed there next week with my twin boys, and I know now I got to bring my sneakers and be prepared to run. Okay, I'm pinch hitting for Fred today, and what we're really going to try to do over the next 20 minutes is deliver about a 20-minute discussion on how phosphorus limits are going to impact your plant, but we're going to try to keep it at about a 10,000-foot level. So in terms of overview, we're going to start off talking a little bit about why and where phosphorus is being regulated, how you can potentially comply with new limits, how it's going to impact your plant operations. And then we'll talk about a few case studies and close out with some discussion. So why regulate phosphorus at all? Well, we all know phosphorus is an essential building block of life and plant and human growth even for that matter. But excessive amounts can lead to all sorts of problems in waterways in terms of algal blooms and low DO problems, fish kills. We've all seen the pictures. This is a great one here on the right. Certainly you can experience plenty of eutrophication problems, and really these impacts affect local streams, small streams, particularly streams with downstream impoundments. So we'll see that in the way it's been rolled out to everybody's permits here in Connecticut. Currently, EPA is taking an approach that they want to return everybody's limit or return our waterways to pre-colonial levels of phosphorus. And in Massachusetts, that's led to limits of around 0.1 milligram per liter. These are really viewed as limited technology-based limits. These are all tied back to the Gold Book standard from 1986 that a lot of folks in the room, I'm sure, are familiar with. And in streams, this means that we're targeting concentration of 0.1 milligrams per liter, but you can see that it gets even lower as you move into lakes. In many instances, in Massachusetts and New Hampshire, other non-delegated states, this has resulted in tight summer limits, and then the limits are relaxed during the winter to about 1 milligram per liter. Here in Connecticut, DEEP's taken a slightly more nuanced approach by evaluating diatom diversity and calculating enrichment factors within each of the receiving waters. And short of going through the math here, the idea is that getting an enrichment factor of 8.4 or less is going to ensure a good algal community diversity in the receiving water. So permit limits end up being based on that as a goal. What that's meant is a number of plants with enrichment factors of greater than 8.4 across the state have received new lower limits for phosphorus. Many of these have been seasonal. And then there's still plenty of folks with no limits who have ocean discharges. They go to the Sound or they go to the Connecticut River where this is less of an issue. DEEP approved this process through EPA back in October 2010, and we're all seeing how it's getting rolled out now. So there's about 45 facilities that have been impacted across Connecticut, and what I've really tried to do here is just kind of highlight the ones that have a cap, which is really just a mass loading limit. And then there's a number of others that are shown in dark blue that are over 1 milligram per liter during the summer, and The light blues are less than 1 milligram per liter during the summer. We kind of chose that cutoff because we think it relates well to a break in what type of treatment you'd use to achieve your goal. So we'll transition a little bit to phosphorus removal basics. And really, this pie chart on the left, there's no numbers on it, I know, but you'll get a quick idea from looking at it that about 2/3 of the phosphorus coming out of a traditional activated sludge plant is dissolved. That's shown in green. And the stuff in blue is particulate phosphorus. So really, to improve phosphorus removal, the solution is going to be to convert more of the dissolved phosphorus into a solid and then remove that solid more effectively. There's a couple ways we can do this. Many folks have looked towards a biological approach. We've said that this is less reliable. We can get into that in a little more detail later in the presentation. But like any biological process, it can be susceptible to upset. Sometimes it can have higher capital costs, but there's certainly folks out there across Connecticut and moreover across New England who have found ways to fit biological phosphorus removal or BPR into their existing plant because they're under capacity. It does require aerated sludge storage if you don't want to re-release that phosphorus that you end up binding up with your biological flock. And it can also compete with nitrogen removal as you're trying to operate your plant. A secondary approach would be chemical, and this is the physical chemical process where you're adding some type of coagulant to precipitate the phosphorus out, turn it into the solid, and then this is a little bit more reliable in many cases. It's really just an issue of finding the right chemical and generating a good flock. It does have a higher operating cost, as you'd imagine, because you're buying more of a consumable material, but it can have some peripheral benefits if you're facing a metals removal number in your permit as well. We've seen this with aluminum and copper and zinc permits that folks are facing nowadays. So again, with either technology, it all comes down to removing the solids. And what we're going to see as we move through this is that a number of facilities end up using a combination of these approaches. So before we get into some solids removal technologies, we'll talk a little bit about what chemicals folks are using. I'm just trying to show the relative costs and benefits of some of the popular coagulants here. A lot of folks will rely on alum or ferric. These are the old standbys, but we've seen a number of plants move towards polyaluminum chloride or PACL in recent years. It's a little more expensive, but it does offer some benefits in terms of a lessened alkalinity or pH impact and a lessened UV impact. One kind of underlying theme here is if you're designing a chemical feed system or chemical addition system at your plant to meet a new limit, you should really keep in mind that you want to design this system for flexibility. You can start out designing for ferric chloride, which is probably the most aggressive of the chemicals on the list here, and you can always switch at a future date to PAC or aluminum if costs shift or if there's an operational reason to do so. We end up advising a lot of our clients to follow that course. So in terms of biological phosphorus removal, a lot of you probably recognize this picture here from the aerobic reactor over through the secondary clarifier. It's pretty much a traditional extended air or complete mix activated sludge system. And really to get BPR, what we've added is a small anaerobic tank on the front end of the process with a hydraulic residence time of an hour or two. It's the same recycle loop that you have off your secondary clarifiers to get back to that anaerobic tank, but this anaerobic tank allows you to grow a population of phosphorus or phosphate accumulating organisms or PAOs. Those PAOs are going to release a ton of phosphorus in this anaerobic tank, but then when they go through an aerobic reactor, they're going to eat up as much phosphorus as they can. When they eat it up, it essentially creates a solid, and then we remove that solid by wasting it out of the secondary clarifiers. Great note on this, though, is that if you have a system where you don't have aerated sludge storage, you're going to waste this sludge out and it's going to re-release all that phosphorus. So if you're considering this, keep that in mind. A number of folks in the room are chasing nitrogen limits as well, and this is just how the same process or the same use of an anaerobic zone could be added to a traditional MLE process to create something called an A2O. That's an anaerobic, anoxic, and aerobic process. I won't go into it in too much detail, but for those of you already doing nitrogen removal, I guess the salient point here is that, again, the anaerobic reactor, if you're trying to carve it out of existing tankage, it's going to eat away at your nitrogen removal capacity potentially. So key concepts to remember with all of this, when adding phosphorus removal to your plant, remember, it will reduce the treatment capacity of your existing plant if you don't add new tankage, and it can compete with nitrogen removal. Also, for limits below 0.5 milligram per liter, you're likely going to require tertiary treatment. By and large, a lot of folks believe that they can get down to 1 milligram per liter plus or minus with some type of BPR approach. And beyond that, you can use chemicals, maybe down to as low as 0.5 milligram per liter. Beyond that, many communities are looking at tertiary systems. We'll talk about those in a moment. One key thing, though, as you're considering an upgrade for phosphorus removal is that, right now, a lot of limits have been issued elsewhere in the region based on limited technology, as I started out saying. And that means that as technology evolves, there's always the potential to get a lower limit once the regulators figure out that we're doing better than we initially thought we would. So we advise a number of folks to design for as low as you can go at this point in time, because with a scalable system, you'll probably end up needing that additional removal capacity in the future. A couple of tertiary treatment technologies that are popular across the region right now, they kind of broke them down into 3 groups here. A number of plants have implemented ballasted flocculation systems. The popular vendors for these are Evoqua with the Comag system and Kruger with Actiflow, and Degremont has the Densideg. All of these processes essentially add a ballast material, be it sand or magnetite or something else. It's a heavy particle, and they use chemical coagulants to mix that in or make it part of the particle with the phosphorus sludge. It settles out like a rock. Cloth disc filters have also become popular, and there's a number of vendors. I don't need to go through the whole list here, but not quite the same removal capabilities as some of the ballasted flock technologies advertise with cloth disc, but there's definitely advantages to the cloth disc being a physical barrier in some instances. And lastly, there's the tertiary activated filter type systems. Blue Pro markets one like this, and that's also been demonstrated to achieve below 0.1 milligram per liter. So at this point, I'll go through a couple of examples. Some of them are plants we're working at, and one of them is not, but I thought it was just a great example to cover here. Fred was actually very familiar with these. I apologize if I screw something up about somebody's plant and you're here in the room, but feel free to confront me after and tell me how wrong I was. This is the Plainville, Connecticut plant, and we're in design on this plant now, trying to get to a 0.2 milligram per liter limit with the potential for 0.1 in the future. Our plan at this point is going to include multi-point chem addition, probably ahead of the SBRs or during actually a settle phase on the SBR. We're going to try to optimize SBRs for enhanced biological removal. And then we're looking at disc filters as a tertiary treatment technology here to meet that ultra-low limit. In Thompson, Connecticut, we encountered a plant that is actually running at about half capacity, and they're trying to get down to 0.7 milligrams per liter. And you look at this plant and you say, gosh, they got all this extra tankage here. Why not use that to do some type of BPR experiment? And what we found is that they don't have aerated sludge storage at their plant currently. And if you wanted to run this in a BPR mode, you'd end up wasting over to this unaerated sludge storage area, and you would re-release all the phosphorus that you had bound up in the biology. So you'd create this vicious cycle where you're just circulating the same phosphorus through the plant, and you'd have trouble meeting your permit. So we ended up going with a chemical addition system at this facility, and that should keep the phosphorus bound up, and it can go out with all the other waste sludge. In Southington, we're looking at a multi-point chem addition system. They have primary clarifiers over the left-hand side of the page, and then it goes through trickling filters. There's some intermediate clarifiers, nitrification reactors, nitrification clarifiers, and then upflow through a denite filter. Some challenges to doing BPR here are all this time in the nitrification filters and the denite filters where we're going to have a low DO environment, and we were concerned about re-release there. So we've proposed a ballasted flock system that is going to be located down here on the site. And we believe that'll get them easily to their 0.7 interim limit and a future limit of 0.2 milligram per liter. So last, I don't want to take credit for this plant. It's not a tie and bond project, but I had the opportunity to tour the Wallingford facility the other day, and I just thought it was such a cool idea. We don't talk about BPR as much on plants that have fixed film reactors like RBCs or trickling filters. But Terry and the other guys over at Wallingford have done some really neat work here through experimentation where they've really converted primary clarifiers down at the bottom of the page into their anaerobic zone where they're releasing all sorts of phosphorus. They go through the RBCs, it gets picked up again, and ultimately they're able to waste it out of the system without using much chemical, if any at all. So their interim limit is 0.7, which I believe they're easily meeting, and they'll require additional work to get to their 0.2 limit. So as you're contemplating some type of phosphorus removal upgrade, there's a couple of key questions you want to ask your engineer. How will my plant's existing capacity be impacted? We talked a little bit about how if you carve these volumes for BPR out of existing process tanks, you're going to be reducing your capacity. Maybe that's an issue, maybe it's not, because you have plenty of surplus capacity. Will I be given flexibility for multiple chemicals? You know, we talked a little bit about how being able to use alum and PAC and ferric at different points in your system may be advantageous, so keep an eye on that. How will the WPCA employees be protected from these chemicals? You know, personal safety is a big issue as we move to these new systems. Maybe many of you aren't adding chemical now, and this is a new thing for you. You want to make sure everybody's got the proper PPE, and certainly that there's adequate eye wash and other safety equipment throughout the plant. And lastly, if I need a tertiary system for low-level phosphorus, you know, that's a fundamental question right off the bat. Does it have appropriate coagulation, mixing, and flock time? And really, as we talked about, we've advocated to a number of people to design a system with enough flexibility to get you to 0.1 milligram per liter or less, because the lower limit is ultimately coming. So with that, I'll